Okay, so the average salary for a church pastor across the U.S. increases as the size of the church increases. The graph above shows the average pastor salaries for various church sizes. We can clearly see a pattern in the data, but the models we have used previously are not appropriate for this data. The grow above displays a large rate of change initially, that's why it's going up quickly, but as the church sizes increase, we see the rate of change decrease. The data above appears to be logarithmic. Just as we have seen with other types of functions, linear, quadratic, and exponential, many real-world scenarios follow logarithmic patterns. Outside of the salary data in the graph above, logarithmic patterns are found in the way we measure earthquakes, sound, acidity, and many other contexts. As a result, we have a need to create logarithmic models for these types of data. Okay, so logarithmic function models. We're doing modeling today, and then we're going to talk about semi-log plots some more as well. Okay, so for a given set of data, the input values appear to change proportionally. What's another way to say that they're changing proportionally? They're changing multiplicatively. We want to be really good with that vocabulary. Multiplicatively. Over equal length output value intervals. Okay, what does that mean? Equal length output value intervals. That means my output is changing additively, because when they're equal length, you're adding the same number each time additively. Okay, then a logarithmic model is appropriate. A logarithmic function model has the form y equals a plus b to the natural log of x, or y equals a plus b log x. So the difference is just your base choice, whether you're doing natural log or common log, where a and b are constants and b is not equal to 0. Okay, selected values of a logarithmic function, so they're already telling us it's a logarithmic function, L, are given in the table above, where L of x equals a plus b to the natural log of x. So they're telling us they chose the model with natural log, base E. Use the given data to write two equations that can be used to find the values for the constants a and b in the expression L of x. Okay, so what two equations could we write with this to find the data? So we can use L of 2, which is a plus b times natural log of 2. And we know that that equals 3, right, from the table. We know the y value is 3. And we can do L of 5, okay, which is a plus b to the natural log of 5, and that equals 7. Good job. Okay, so those are going to be my two equations. Writing the L of 2 and L of 5 at the beginning, I would argue, is optional. These are the two equations we're actually going to use to solve it. It's a system of equations. This one, since we already have the a's isolated, let's try just subtraction. And you can use any method for solving systems that you want, but let's just go ahead and subtract. So let's go ahead and subtract that first one from the second one down here where they're wanting us to actually find the values. So I'm going to do a plus b natural log of 5, natural log of 5 equals 7, and I'm going to subtract a minus b natural log of 2 equals negative 3. Okay, so I'm just going to subtract that from the line above. So my a's cancel. 7 minus 3 is 4. Now, this is just straight subtraction. Did you guys remember that that's just b natural log of 5 minus b natural log of 2. Nobody tried to do any bad combining that would have been illegal? Did we all have our heads in the right place working on that? Hopefully. Okay, and so now we would just want to solve for b. Now, I know you're really tempted because we're in log mode. You see that minus, you want to think, products, and you want to start making this a quotient. That's not what we're trying to do here, guys. We're trying to solve for b. Right now, every term with a b in it is on the left side. So what should we do? Factor out the b. That's why we want every term with the b on the same side. So factor out the b, and that gives me natural log of 5 minus natural log of 2 equals 4. Okay, and then we want the b by itself. So last step is just to divide both sides by whatever b is multiplied by. So b is just going to be 4 over natural log of 5 minus natural log of 2. Now, again, you might be tempted to use the quotients, but there's no reason to simplify for that. We're actually trying to find these values, and so we're just going to go ahead and simplify and find them. So we're going to put that in our calculator. B equals 4 over natural log of 5 minus natural log of 2. And guys, for time's sake, do you mind if I just give you that number? We'll do some things in our calculator, but I'm going to give you some of these just to speed you up a little bit. So this is going to be 4.3654. And I put the 4 just so that if you're truncating or rounding, you can tell what your 3 digits should be. Also, at this point, I'm going to put the dot, dot, dot because we would want that full B value. So on your calculator, when we go to use this, we would copy the entire value until the end of the question. So if this is the end of the question, if that's all they want, then we could round to 3 decimal places and put that. But that's why some of the answer keys will show 4 decimal places. They say they grade only the first 3, but then you can see if truncating or rounding if your answer would have been correct. Okay, so now that we have B, so that's approximately B, we need to go back and find A. Okay, so let's plug into our other equation. We here, if going back to this equation, so if I want to get the A by itself, all I have to do is subtract the B natural log 2 from both sides. So that gives me A equals 3 minus B, we now know is 4.3654 dot, dot, dot. Okay, natural log of 2. And if we put that in our calculator with that full B value copied, okay, so you would copy the full B value and use it in its entirety, okay, that's going to give us an A of approximately negative 0.0258 dot, dot, dot. Okay, so that'll give us an A value there. Okay, we all feel like we can solve systems of equations. Even though our equations now look more complicated, it's still the same algebra to do it. Yes, ma'am? Yes, right, because we do want decimal approximations for this, and so you'll have to use a calculator because those aren't exact logs. Those aren't exact values, okay? All right, so let's move it along to the next page. Okay, so here we do actually want to get our calculators out. So if you're using your Desmos calculator, get your Desmos calculator out. If you're using the TI, then you've got the instructions there on your page for the TI calculator. Let's put this data in our calculators. Let me see. Get it. I'll try modeling with the Desmos since more of you seem to pick the Desmos. By the way, I was talking to the AP teachers. They said for retakes, it'll be easiest if you guys just use the TI calculators. So make sure that you're paying attention and practicing with both because so first of all, I tried using Lightspeed to monitor after school yesterday for a retake, and the admin blocked after school hours. So during the retake that's only 45 minutes after school, I couldn't use Lightspeed to restrict it, and they wouldn't have you in their classes anyway to restrict it. So they said for retakes, if you need a retake, that it's going to be best if you just use the TI calculators. So make sure that you practice those as well. Okay. All right. So let's go ahead and get, you guys don't want that one. That's the baby Desmos for the SOL. Let's get the full Desmos calculator. Okay. And so let's put our data in here. So let's go ahead and add a table. And let's read the problem first. So this is the table above gives the data from the graph at the beginning of the notes, related church size and average salaries for pastors in the United States. It says use the regression capabilities of your graphing calculator to find a logarithmic function model. So we don't have to choose the model. They're telling us to use a logarithmic function model for the data above. And so you can see right there, if you're using the TI-84, that you're going to use the linear regression. That's the natural log regression choice 9. But let's go ahead and try it on the Desmos as well. So I'm just going to put in my data, 75, enter 120, enter 250, enter 300, enter 450, enter 650, enter 900, enter 1500, enter 2500, enter 5000, enter. Okay, then I'm going to scroll over and up. Okay, we've got 42, enter, 58, backspace, 58, enter, 70, enter, 79, enter, 88, enter, 95, enter, 110, enter, 125, enter, 138, enter, and 175, enter. Okay, and then we're going to go up and use our regression option. So it's sitting right here, that little symbol of the curve that's fitting the data points. So, and they said to use logarithmic regression. And so we're going to choose logarithmic regression, and we are going to make sure we check the log mode button. So log mode should be used for exponential functions, for logarithmic functions, and for power functions is what it said on the Desmos regression page. So we'll make sure we click it for those 3 options. Okay, and so what did we get for our equation? 9542, 29.08. Okay, so we got y equals, or S of p, I'll correct that to S of p. So S of p, the salary, based on parishioners, is going to be negative 91.542, and I'm going to put dot, 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 because we would still use all the numbers, plus 29.908, and I'm going to put dot, 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 because we would still use the additional numbers, times the natural log of x, So there's our equation. Then it says, using the model found in Part A, what is the predicted annual salary in thousands of dollars? And by the way, let's go look at this. Okay, it is given in thousands of dollars, so we don't have a conversion that we need to do there. Okay, so that already is given in thousands of dollars. For a pastor whose church size is 500 people. Okay, that means we just want S of 500. We want S of 500. So let's go back to the Desmos calculator and practice that. So Desmos calculator. Okay, so I'm going to use the little notebook paper thing to copy my statement there. Now, right now it's a y equals, and I want to go back and change it. So there's different options of how you can do this. If you're only doing the one, we could just change our x value there to 500, but I'm going to come back here and I'm going to change the y equals to f of x notation. That way, if we needed to use it more than once, and then we can go find f 500. Did you guys know that you could do it that way? Okay, and so we should get 94.32 3295 dot 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 94.3295. That's beautiful. Oh, very, very interesting. Very, very interesting. Okay, good. Which is, I'm happy to say, which is the exact same thing that you'll get on the TI calculators. Yesterday, when we got it, we got a slightly different number, and we had log mode checked and everything. We were worried that maybe, but it must have been there must have been a data error entrance that we missed. Okay, so that's good to know. All right, so so I just did this on data. Didn't you get this? On the Desmos calculator?
No, on the TI.
Okay, so 94.3. So on the TI, you've got the screenshots on your notes of the TI calculator, and they got 94.3295. Y'all don't have the screenshots on yours? Okay, so maybe I thought the screenshots were on there. It's on the answer key, so I'll post it. They also got 94.3295, so I would say go back and check your data, because just like yesterday, the people who were getting slightly different on the Desmos probably had a mistake. Okay, uh-huh.
So we get 94.3295, but after that it's different.
Yeah, after that you have 403. Yeah, that's right. And so I think one of the problems, so this is what we were talking about yesterday, and I don't want to take much class time to get into this because we have a lot of notes to cover. These are new features for the Desmos calculator, and we don't know how exactly they're doing their calculations. So a student came to me and showed me a log regression plot, because we can have it now plot the regression graph for this. The residuals, that's the word I was looking for, the residuals graph. And when he did the residual from the graph, which it does for you, it was different than when he did the residual by hand. And I think what the difference is here in our calculation of f of 500 is because when we copied it and used this equation here, I think it clearly truncates the answer. And I think that's why we're getting the difference. Whereas in the TI calculator, we know it stores not only what's on screen, but 8 digits past that, and it uses all of those digits when it makes the calculation. And so I think, they've just added these features to the Desmos. I hope they'll continue to get better and better, but we are going to be okay to 3 decimal places, and the Desmos is going to be the embedded calculator on the AP exam. So they'll have to take whatever the Desmos gives you. Okay. And so don't worry about those kind of things. I think they'll get that stuff worked out. But just want to make sure that we're all on the same board here. Okay. So let's go answer the question. His salary is approximately 94, and here, because it's an approximate, we're going to go ahead and list it as 3295 ... thousands of dollars. So we do want our units. This is a final answer, so if you rounded it to 330, or if you truncated it at 329, both of those would be okay as well. Thousands of dollars. Question, Arjun?
Yeah, so like for just honesty, it's like showing less decimal. Like it's only showing like the thousandth place on this logarithmic regression thing.
Right, and that's why I think we're getting more. I think that's why we're getting a bigger error on the Desmos calculator. That's what I think too. But we'll see. Okay. All right, so let's go ahead and try our next problem. It says the most common and preferred method to measure in sound intensity levels is in decibels. The sound intensity levels in decibels of a sound having intensity I in watts per meter squared is modeled by the function the decibels of I is A plus B times log of I. Okay, fun fact down here in the corner, the word decibel comes from two pieces of information. Deci refers to the fact that the level of sound found in is multiplied by 10 as part of the formula, and Bell refers to Alexander Graham Bell, the inventor of the telephone, and the person decibels are named after. Okay, so fun fact for you. Okay, and it's in the above equation, that's where A and B are constants. So it says the sound of a noisy traffic has intensity 1 times 10 to the negative 5 watts per meter squared and corresponds to 70 decibels. Okay, what they're giving us here is they're giving us specific I and B of I notation. So this is like our X, Y chart. They're giving us 2 data points. So the intensity of the sound is 1 times 10 to the negative 5th. And that is 70 decibels. 1 times 10 to the negative 5th, and that's 70 decibels. A loud concert has an intensity of 1, so the intensity is 1, and it corresponds to 120 decibels. Okay. Use the given data to write 2 equations that can be used to find the values of constants A and B in the expression B of I, and then find those values. Okay, so we're going to just get a little bit more practice with this, so let's go ahead and do that. So our 2 equations are going to be our 2 data points. So B of 1 times 10 to the negative 5th, and B of 1. Okay, so plugging into our function model, that's going to be A plus B log 1 times 10 to the negative 5th. And that's going to be A plus B log 1. Okay, which of those looks easier to start with as we're trying to solve for our variables? Yeah, log 1. Not just because the number is smaller, but because what is the log of 1? Yes, very nice. Remember, that's common log, so it's base 10. So 10 to what power gives you 1? 10 to the 0 power. Anything to the 0 power is 1. So that goes to 0, and anything times 0 is 0. So that whole term goes to 0. Oh, and I should have finished my equations here. This is equal to 70 on the first one, and this is equal to 120. Okay, so this first part is optional to write. This second part, this is what the equations that we're actually using. So I was just showing you where they came from, but these are the equations we want to solve. So that automatically gives us one of our answers. A is 120. So A is 120. So that was nice and easy. And now we want to go back and find B. So we've got 120 plus B log 1 times 10 to the negative 5th equals 70. And this one's also not too bad, because what is the log of 1 times 10 to the negative 5th? Well, remember, multiplying anything by 1 is just itself. So that's really just 10 to the negative 5th in there. And so I'll go ahead and rewrite that. 120, to make this a little bit more obvious for you, times log of 10 to the negative 5th. Okay, equals 70. Let's evaluate that log. 120 plus B times, what is the log base 10 of 10 to the negative 5th? What power do you raise 10 to get 10 to the negative 5th? Negative 5. You got it. That there, our base of the log and our base of the exponential expression are the same, so they undo each other, and it's just negative 5, and that equals 70. So if I subtract 120 from both sides, that gives me negative 5b is negative 50. If I divide both sides by negative 5, that gives me b equals positive 10. B equals positive 10. So we found A and B. So let's go ahead and put those together in an equation to help us with the next part. Okay, so we've got A and B, and I need my function model there. Okay, there's my function model right there. Let's go ahead and write it here at the top. So B of I, the decibels at a given intensity, is A, which we said is 120, plus B, which we said is 10, times the log of the intensity. Give me just 1 second. I can check. my phone for you in just a second. Okay, so it says the human eardrum can burst when the sounds reach an intensity level of 1 times 10 to the 4th watts per meter squared. According to the model found above, what is the predicted number of decibels required to burst a human eardrum? So let's go ahead and plug that into our equation and let's check that. For those of you quizzing, you've got 2 minutes left. 2 minutes. You can just stick it in the thing. Okay, so we said reach an intensity. Okay, so we just want the decibels at 1 times 10 to the negative 4th. Oh, sorry, not negative 4th, to the 4th. And that's just going to be 120 plus 10 log 1 times 10 to the 4th. Okay, so let's evaluate that. 120 plus 10 times, what is the log base 10 of 10 to the 4th? 4. You got it. You got it. Using those properties. Okay, so 40 plus 120 is 160. And what are our units? Decibels. And I think it's a D with a B, but since I'm not sure, I'm just going to write it out. I don't want to offend our science teachers with the wrong notation. So 160 decibels there is the correct answer. Okay, so just a little practice with logarithmic applications. Let's do some compound interest. Okay, so a quick recap of what our abbreviations mean. When we're doing interest in particular, instead of doing the initial amount at times 0, they use the letter P, which stands for principal. But the principal is the original amount. It's the amount at times 0. They just use the principal wording for that specific type of application. A is the amount in the account after the interest is added. So usually we often refer to this as the amount at time t, because this is a function of time. Okay. R is the rate, and we're going to need it as a decimal, which means we'll have to Dr. Pepper it. If they give it to us as a percent, we'll move 2 places to the left to make it a decimal. And then when we give our final answers, which we'll solve for as a decimal, we'll change them back to percents by moving that decimal place 2 places to the right. Okay. T is the length of time in years, and that's time for those of you that are quizzing. For interest applications, time is always in years. Time is always in years for our interest applications, unless we do a rate conversion. Okay. So Avi and Om, I need your quizzes. Okay. And if you'll just set them right there for me. Thanks, guys. Okay. This is a perfect place to join us in the notes. We're just doing the compound interest part. Okay, N is the number of times that is compounded annually. Because time is in years, so it's just the number of times in a year that it's compounded. So if it's compounded annually, that's once a year. If it's compounded quarterly, 4 times a year, semi-annually, twice a year, monthly, 12 times a year, and daily, 365 times a year. So we're not worried about leap year years. We're going to use 365 for daily. Okay. Now, if it's compounded continuously, we're going to use the formula with E in it. This is for compounded continuously. Compounded continuously. Don't talk about it right now. Let's go ahead and get going on the notes. Okay, so sometimes people just call this PERT, and that's because it's principal times E to the rate times time. Principal, so the amount equals the principal times E to the rate times time. Okay, and that A is also the amount at time t. Okay. And so E, remember, is Euler's number. It's not a variable. It definitely keeps going. And so we'll use our E button on the calculator to do that. Okay, so let's try a couple of problems real quickly. It says, what would the rate need to be for $300 invested 4 years compounded continuously be to be $1,200? So if we've got $300, we've got 4 years time, and we need it to grow to $1,200, what kind of a rate do we need to secure? Okay, so which formula are we using? Yeah, because it's compounded continuously. So we're going to do the amount at time t will equal the principal times E to the rate times time. When you write those, I highly recommend that you kind of say to yourself, like I just did, what those variables represent so that you get familiar with them. And I always like writing my formula before I plug into it. It just kind of helps me learn them as well. So we want $1,200. We've got $300 as our principal to put down. We are solving for the rate we'll need. And how much time do we have? 4 years, 4 years. Okay, so let's solve for that rate. So to solve for it, since it's up in the exponent, we'll have to use logarithms to solve for it. But let's go ahead and get started with that. We're going to divide both sides by 300. 12 divided by 3 is 4. E to the, I'm going to write it as 4r. You can leave it as r times 4 if you want. Okay, and now we're ready to, what should we do next? Right, rewrite it in logarithmic form. Can you give that to me, Vinay? What should that look like? Perfect. And then last step, to get r by itself, divide both sides by 4. And I'm going to get it, my rate equals the natural log of 4 over 4. Now, if I was going to use this in another problem, I would keep it in exact form just like that. But because we want the rate as our final answer here, we're going to go ahead and get a decimal approximation of that. It's going to give you a decimal, 0.34657. And I'm just helping here to save us time on calculators. I'll tell you when you actually need to do it. But if you want to practice in your calculators, you're welcome to, just for the calculator practice. Okay, is that my final answer? Am I ready to box it? No, because that's my rate as a decimal, but we don't report rates as decimals. We report them as percents. And so I have to move that decimal place 2 places to the right to get it to be a percent. So it's going to be 34.657%. Okay. And so I used enough digits so that when I move the decimal, I still have 3 digits of accuracy in my decimal percentage. Okay. So 34.657%. Good luck finding an interest rate of return of that. Okay. It's very hard to earn that much money on your investments. Okay. All right, let's go ahead and take a look at the next problem. It says, how long would it take for $2,000 to triple if 5% interest is compounded semi-annually? Okay, which formula are we using? Okay, it says compounded semi-annually. So that means we have an n, the number of times per year it's compounded, and semi-annually means it's compounded twice a year. So n equals 2. So we're using our formula that the amount at time t will be the principal or initial amount times 1 plus r over n to the nt. Okay, so let's plug into that. It says we want it to triple. Now, tripling $2,000 means it would be $6,000. And you can put $6,000 over here, okay, equals the principal we said was $2,000. 1 plus our rate, they said is 5%. So that's going to go into my equation as 0.05 as a decimal. Remember, we have to convert it. We said the number of times per year it's compounded is 2, and that's raised to the 2 times time, and we're solving for time. Now, I said you could put it in your equation like that. You could triple the number yourself to see what the output should be, but you can also work this problem in percentages. And what I mean by that is you can say we need the principal, the original amount is 100% of the investment. So just putting a 1 for our principal, which means if we wanted to triple, it would be 300%. And 300% as a decimal is 3. Okay, so think of it as percentages. 100% is 1, and 300% is 3. So you can do that, and then it's still just times 1 plus 0.05 over 2 to the 2t. Okay, and then you can solve it from there. In fact, that's the first thing we're going to get when we start solving it this way. When we divide both sides by 2,000, and let me not cover up my equation when I do that. When we divide both sides by 2,000, 2,000 over 2,000 cancels, zeros cancel, 6 divided by 2 is 3. And so we have 3 equals, 1 times that is just going to be 1 plus 0.05 over 2 to the 2t. Okay, and so we end up with the same thing. Okay, so you can start at that second step. If you remember, that's just percentages. That's just doing it as percentages. Okay, all right, so let's go ahead and finish solving for it. What should I do next? What am I ready to do now? What am I ready to do? A little bit louder for me, Vinay, I can't hear you. No, we don't need to. We're going to keep it in exact form, so we don't need to, okay? I'm ready to write it in logarithmic form. We just have a really big base. And the beautiful thing is the Desmos calculators can now do that. The TI calculators could always do that. And I tried it for these notes, and the Desmos calculator can now do those bases. So that's really exciting. You used to have to do it on a separate line and then copy and paste it in Desmos, but now you can do it right in Desmos. So let's all get our calculators out, and first of all, let's write it by hand, and then let's try putting it in our calculators. So what should that look like? That should look like log base. What's my base? 1 plus 0.05 over 2, you're right, of 3 equals 2t. Okay, and so while we're at it, let's go ahead and finish solving this by hand before we put it in the calculator so that we'll be ready to get final answers in the calculator. I'm going to divide both sides by 2 to get t by itself. Okay, so t is approximately, and let's put all of this in our calculator. Okay, let's put that whole side in the calculator. X out, maybe. Okay, not sure. I think my calculator froze. Reload. Okay, good. There we go. So we're going to choose the log option where we get to enter the base. So I'm going to scroll down to log base A, and I'm going to do a parentheses for my base. I want the 1 plus and the 0.05 divided by 2. Scroll over, close my parentheses for my base. Scroll over and over into the parentheses for what we're taking a log of. Close that parentheses and divide it all by 2. Okay, how'd you do? Did you get it in your calculator correctly? It's a beautiful thing. So our time is approximately 22.245, and what are our units there? Years. That's time in years for our application. So 22.245 years. Questions I can answer about that? Okay. Because this is time. Okay, right, versus rates. Rates have to be converted to go into into equations. So in equations, rates look like decimals, but when we report them back as percents. Okay. All right, so let's take a look at another couple problems real quickly. Growth and decay. Now, growth and decay problems, once you get a little experience with these, you should start to realize that they're the same problems, just with a different type of application. So here, this amount of time, the amount with growth and decay should look like the PERT equation. So that's just amount. They used principal for the initial amount times e to the k is our growth factor. And so they used an r for their growth factor times time. So it's the exact same equation. It's just exponential growth or decay. It's just that for interest, they customize their variables to their financial application. Okay, but it's the exact same idea. The culture contains 1,500 bacteria initially and doubles every 30 minutes. Find a function that models the number of bacteria after t minutes. Okay, they want these to be a function of time. But right now, do I know my growth factor? Do I know my growth rate in this problem? I don't know it yet. I do know that it doubles every 30 minutes, which is plenty of information to find it, but I don't actually know what it is yet. So remember, you often will have to solve for K first. You'll have to solve for your growth factor. If they tell you doubles, triples, has a half-life of, you're going to have to solve for what the growth factor actually is. Okay, so let's go ahead and do that. Let's try to do that. So they said it doubles every 30 minutes, and we're not in interest anymore, so we don't have to use years for time. We can use whatever units they want. And so what would that equation look like? Should we do it in percents, or do you guys want to use the actual numbers? Okay, let's use the actual numbers if you're more comfortable with that. Okay, so we want the amount to be double that. So what would the doubled amount be? 1,500 doubled would be 3,000 equals the initial amount was 1,500 times e to the, we don't know the growth factor, but we're going to solve for it. What's the time it takes to double? 30 minutes. So I'm going to put 30 in there, and remember that my time is in minutes. Okay, let's solve for K. Let's solve for that growth factor. I'm going to divide both sides by 1,500. I should have asked you guys what we're going to do. 1,500s cancel, 0s cancel. 30 over 15 is 2 equals e to the 30k. Remember I said if we had started in percentage, we would have put 2 here for 200%, and we would have put 1 here, which if no coefficient is written, it is a 1 for 100%. So that's what I meant about did you want to do it in percentages or did you want to use the actual numbers? But either way, you'll get that as your second step. But you are legal to start there as your first step if you want, okay? All right, and then help me from there. What should I do next? Julian, what should I do next? And that's going to look like, okay, but we don't say ln. We write ln, but we say or natural log. If we're going to write ln, if we want to write log base e, we'll write log base e. If we want to write natural log, we'll write ln, okay? So natural log of what equals, beautiful, okay? Last step, divide both sides by 30. Now here, we're 100% leaving it in exact form. So K is just our growth factor, natural log of 2 over 30, because we're only using it as an intermediate step. Okay, we want that. We're trying to build the equation. So we're 100% going to leave it in exact form. So what should my equation look like? My equation should look like the amount equals the initial amount, which they said is 1,500. I've got some stray marks up there. Those are not part of my equation. Okay, so it equals 1,500 times e to the natural log of 2 over 30 times time. So there's my equation. Okay, after how many minutes will the culture contain 4,000 bacteria? Do you guys think you could do that? I don't think we probably need more practice with that. Do you guys think you need more practice with that? Yeah, we do. We want more practice?
Why don't we simplify the ln 2 over 30?
Because we want to leave it in exact form. We don't want to get a decimal approximation. It doesn't simplify. Did you think it did simplify?
I thought we could look for the calculator.
No, to get a decimal approximation. We're not going to get a decimal approximation here because it's not our final answer. So we're going to keep it in exact form 100%. 100% we're going to keep it in exact form. Okay, so do you guys need more practice with this or not? Yes, no, maybe so? Okay, I think not. Let's go do B because so we're going to skip this, but it's in the notes if you want to see it for extra practice, but let's do B. I want us to do B. It says find the number of bacteria after 2 hours and round to the nearest whole number. Okay, so this time it did tell us round to the nearest whole number for the bacteria, so that told us we'll be using whole numbers. But let's go ahead and set it up. You're like, Miss Weaver, why are you having us do this? This is very easy. The amount after 2 hours. So what are we plugging in for T?
2.
No, it's not 2. It's not 2. That's why Miss Weaver had us do it.
4.
They said hours. What are our units? Minutes. And so 2 hours is 120 minutes. Be careful about your units. Always kind of flag them whenever you find them and make sure that they align. So we want the amount at times 120, which is just going to be 1,500 times e to the natural log of 2 over 30 times 120. And I don't really need you to actually put that in your calculator to practice, but you sure can. I'll let you put it in there real quickly just for the practice. They said we're rounding to the nearest whole number, so we're going to call that, tell me when you get it, and it's good to practice raising your e's to fractional exponents, all that good stuff. Make sure that you get it in there correctly. Oh, you're not going to practice? You think you're a calculator pro? Never going to have a mistake?
I was just reading through the problem.
I would practice. Like I said, these are some of the hardest. I would say what we do in exponential and logs unit are the hardest things we're going to do on the calculator. So making sure that you can do them correctly is important. Yashi, you want to try it? Do you have an answer, Justine? What'd you get?
184.
That is not what I got. What'd you get? That is not what I got.
I got 24,000.
I got 24,000 as well. 24,000 bacteria. He is a calculator pro over there.
Let's go.
Okay. I guess I should have been doing it on my calculator. Are y'all on Desmos calculators having problems or TI? Which one do you want to see?
I think it's TI.
Which one? TI? Okay, let's pull it up on the TI real quickly. Okay. It's just taking a minute to pull up my calculator. We'll run through it. Okay, I always reset my calculator before I get started. Okay, we want 1,500. And then the e to the x is such a common use that it's right there, second natural log, because those are inverse operations, so they're on the same key. And it already puts the e in with the power. It's ready for its power because it knows you want to raise it to a power. I'm going to do alpha y equals up there so that I get a fraction in my exponent. So the green alpha key and then y equals. Now I want natural log of 2, close parentheses, scroll down to your denominator, over 30, scroll out of your fraction, times our time, which we said was open parentheses 120, close parentheses. And so you should get 24,000. And it's not even approximate. We didn't even have to round. So that means Miss Weaver can change her approximate sign. I thought we were going to have to round to the nearest whole number. It's going to be 24,000 bacteria. Going to be 24,000 bacteria. Okay, did that take care of us? Everybody got it fixed on their calculator? It just takes practice. All right, so let's talk Newton's law of cooling real quickly. Okay, the formula is here. It says the temperature of a heated object at a given time t can be modeled by the function u of t equals t times u sub 0 minus capital T times e to the kt, where k is less than 0, where T is the constant temperature of the surrounding medium. Now, that's the nice formal word for it. We usually think of this as room temperature. This is the temperature of the room you're moving it into. It's the temperature of the room you're moving it into. Okay, U sub 0 is the initial temperature. Okay, so that's the initial temperature of the object, and K is a negative constant. Okay, kind of like our growth factor. So that should look familiar, that E to the KT, right? That's the continuous cooling. Anything that's continuously changing is going to have the E in the formula for it. Okay, so our problem is actually on the next page, so let's rewrite that formula at the top so that we have it handy and ready to use. It says U of T, or the temperature, okay, is going to be capital T, which is room temperature, plus the initial temperature, U sub 0, minus room temperature, so the difference between the temperatures of the two things, times E to the KT. Okay, and again, it's nice to kind of think of what those mean as you're writing them. It'll help you learn it. Okay, lowercase t is time, capital T is room temperature. Okay, so it says, write the equation if the thermometer, okay, it says a thermometer reads 72 degrees Fahrenheit. Now, I know you're thinking that that's the room temperature. Let's read what is next. And it says, and it's put into the refrigerator. So the thermometer is actually the object that's going to be cooling. It's the object that's going to be cooling, which makes 72 degrees, it's initial temperature. It's U sub 0. It's initial temperature. And it's put into a refrigerator where the temperature is a constant 38 degrees Fahrenheit. That is our capital T. That's our capital T for the temperature of the medium that it's being placed into. So it says, write the equation if a thermometer reads 60 degrees Fahrenheit after 2 minutes. Okay, do we know our growth factor? Do we know our growth factor? No, but they just gave us enough information to calculate it. They said it reads 60 degrees after 2 minutes. So that's enough information to find it. So let's find our growth factor. Like I said, you often have to solve for K first. You often have to solve for K first. All right, so let's go do it. So it says the temperature of the object is 60 degrees. So that's the temperature after a time of 2 minutes. Our initial temperature was... Oh, sorry. We want our room temperature first. Room temperature is 38 plus our initial temperature was 72 minus our room temperature, which is 38 times E to the, we don't know K. That's what we're solving for. How long did it take? What was the time to get to 60 degrees? 2 minutes. Okay, so we are in minutes, so that's 2. All right, and let's solve for K. So help me with that algebra. Can you get us started? What do I want to do first? Yashi, what should I do to start trying to get that K by itself? That's right. We're going to subtract 38 from both sides. That's going to give me 22 equals 72. Oh, let's go ahead and do that. 72 minus 38 is going to be, thank you, 34 times e to that. And I'm going to go ahead and write it as 2k. It just looks right to me. All right, what should I do next, Tom?
Divide 34.
Divide both sides by 34. Now, two little things. You do not have to simplify in intermediate steps. And in a way, you maybe shouldn't, because it just is one more chance to make a mistake. You're going to be going to your calculator anyway, but sometimes we can't help ourselves. That is screaming out to me, I'm going to simplify it just because my brain can't not simplify it. What is that? But you don't have to change it to 11 over 17. You can 100% leave it as 22 over 34. Except for if they ask for the growth factor as an answer, maybe we should simplify it just so that it's fully simplified. Okay. All right. So that equals e to the 2k. And what am I doing next? Rewriting it in logarithmic form. Can you help me with that? What should that look like, Regini? Okay. Oh, sorry. You said equals 2k. I was like, wait, why do we still have an e in there? It's because I missed my equal sign, and then I was not paying attention. Equals 2k. Okay, that looks better. Last step. Divide both sides by 2. And so there's our k value. What did they ask us for? They asked us for the full equation. We know that our k is natural log of 11 over 17 over 2. Okay, but they want the full equation. So let's put it together into a full equation. That'll look like u of t equals 38 plus 34 times e to the natural log of 11 over 17 over 2 times time. And I think they should have put a lowercase t there. That's because it's a function of time. So it should have been a lowercase t in that formula. Okay, so we're going to skip the next two because it's just more practice manipulating equations. We've done a bunch of that today, and I think you guys are probably pretty good at that. If you want more practice, go back and do them. They're good problems. There's nothing wrong with it. Okay, any questions for me on that one before we move on from it? We feeling okay with this? You'll get very good at solving those what look like very complicated problems because they do just kind of solve the same way every time. Okay, so let's talk about a logistical growth model. The logistical growth model is an exponential function that models a situation where growth is limited. The carrying capacity C is the maximum amount that the situation can support. Okay, so let's pay attention to that. The carrying capacity C is the maximum amount that the situation can support. Now, I thought it was interesting that it's called the logistical growth model when they said it's an exponential function. So I went to look for why they called it an exponential function, and there it is. In the denominator, the variable is up in the exponent. So that's why they called it an exponential function, okay? So let's take a look at it. It says logistical growth model is the population P after time T obeys the equation P of T equals C over 1 plus A times E to the negative BT, where A, B, and C are constants, and B is greater than 0, and C is greater than 0. Okay, so that's true. That's the generic model for logistical growth, and you can see it usually has to do with populations over time, but this application that we're going to use is actually for the number of items at Best Buy. So let's see how they use that. And this, again, is how your problems are usually given in AP format, where they take you. It's not that you needed to know the generic formula. They gave you an application of the formula. Okay, so it says the logistical growth model P of T equals 0.90 over 1 plus 3.5 times e to the negative 0.339t. And this relates the proportion of new personal computers sold at Best Buy that have Intel's latest coprocessor T months after it has been introduced. T months after it has been introduced. Okay. So let's answer some questions. What proportion of new personal computers sold at Best Buy will have Intel's latest coprocessor when it's first introduced? So when it's first introduced, they gave you a little hint there. Okay, that's when time is 0. That's when time is 0. So let's go find that. Let's go solve for that. So that just wants P of 0. So that's just going to be 0.90 over 1 plus 3.5 times e to the negative 0.339 times 0. And we said anything times 0 is 0. So that part goes to 0. Anything to the 0 power is 1. And anything times 1 is just itself, right? But we don't have to finish solving this by hand. So while it is fun to simplify and use our things, we can just go ahead and put that in our calculator to get a final answer. So I will help you guys with that to speed us along. Okay, so that is just going to be, I got 0.2. Now we're, and that, so I needed to point out in this problem, it says this is the proportion. So is it saying 0.2 objects? No, we got to convert that to a percent. That is 20%. It's the proportion. So the part of the whole that will be have the new Intel coprocessor. So 20% of them, as soon as they're released, 20% of their stock will have the latest coprocessors. Okay. Okay, it says determine the maximum proportion of new personal computers sold at Best Buy that will have Intel's latest coprocessor. So what's the maximum amount? We know the starting amount. What will the maximum amount be? Well, remember what the definition of the formula told us. The carrying capacity is the maximum it ever can be. So we don't have to do any calculations there. 0.90 is the carrying capacity, and that means the greatest amount that they'll carry will be 90%. So 90% is the maximum that will be carried. Okay. All right. And let's go ahead. Should we do this next one? When will 0.75 or 75% of new personal computers sold at Best Buy have Intel's latest coprocessor? Should we go ahead and try solving that one together? Yes, no, maybe so? Okay, let's do it. Okay, so what are we doing? We're plugging 0.75 in for our output. So it is in decimal form in our output. So that equals 0.90. I was just trying to see whether or not you guys felt like you needed more practice solving. But it's good to go ahead and solve this one together because it is in the denominator. It's just slightly different algebra. You guys know how to do it, but we can try it together if we'd like. -339, and we're solving for the time when that'll happen. So our time is going to stay a variable in our denominator. All right, let's start solving for that t. Okay, so when I see this problem, I just automatically want to do the fastest way to solve this problem. And I'm not sure how many of you also see that this is the fastest way to go after t. Do you guys see to just switch the position of those two? Okay, some of you have seen enough of that you know that that's what we're going to do. If you haven't seen enough of that, we know we want to get rid of the denominator, so we're going to multiply both sides by the denominator. When we do, that's going to put this denominator on this side. Do you agree? And then the next thing we're going to do is divide by this to get rid of it. So it just switches the position of those two. It just switches the position of the two. If that doesn't make sense to you, go ahead and do those 2 extra steps. They're not extra. They'll still get you to the right place. But I can't help myself. I'm just going to go ahead and write it as 1 plus 3.5 times e to the negative 0.339t equals 0.9 over 0.75. All right, let's keep going. We want to solve for t. What should I do next? Subtract 1 from both sides. And if you actually do that in your calculator, or if you want to do this by hand first, it doesn't, if you wanted to simplify that by hand first, that's 1.2 when you subtract 1 from both sides. So do it in your calculator because you don't have to know that it's 1.2 first. You can do it in your calculator. What do we get over there? 0.9 over 0.75 minus 1. Yeah, we get 0.2. Next step. By 3.5. Remember, I asked you guys whether or not we needed to do one more of these, okay? And so that gives me e to the negative 0.339t equals 0.2 over 0.35. Now, if you want to, just to save yourself, we can leave it exactly like that, or to save yourself having to write those decimals, that would be the same as 2 over 35, right? That would be the same as 2 over 35 if I just want to write it as whole numbers rather than decimals, but you can keep the decimals. Both ways are okay. Those are equivalent fractions, so you can do it either way. All right, and then I'm ready to write it in logarithmic form. Write it in logarithmic form. So help me with that. Arjun, what should that look like?
Natural
Of?
log of 2 over 35
Mhm.
equals negative 0.332.
Beautiful. That means our last step to get t by itself. Divide both sides by negative 0.339. Put that in your calculator for practice. Natural log of 2 over 35 divided by negative 0.339. Do you have it? I agree. And what is our units for time? We remember we need 3 decimal places and we need units. Time is in months. You're right. Time is in months. Yeah, no surprise that they don't measure that in years because innovation continues to roll out so quickly, right? They'll have a new coprocessor years from now. Okay, very nice. So are we feeling pretty good about solving logistical problems? I'm feeling pretty good about it. Hopefully you are too. We're going to skip our brain break. So sorry, but just because of time, I'm worried about how finishing on time. So if we finish, we can do it at the end. Okay. So let's talk semi-log plots. This first whole half of the page is a re-summary of the stuff that we've already talked about. So you can read back over it if you want, but we're going to skip that whole first part and go back down here to this first example at the bottom of the first page. Okay, so that literally was a recap of what we've already talked about semi-log plots and their graphs. Okay, all right, so this is a semi-log plot. It says, after Mr. Barwell tells another one of his hilarious math jokes, it begins to spread around the school. The number of people P that have heard the joke after T minutes is graphed on the semi-log plot above, where the vertical axis has been logarithmically scaled. Which of the following functions could be a model for P? Okay, first of all, let's look at that graph. It looks what? It looks what? It looks linear. And if it looks linear on a semi-log plot, what does that mean? That means it's exponential. It means it's exponential. Okay, so which two answer choices can I eliminate? This is multiple choice. Which two answer choices can I eliminate right away? A, because that is linear, and C, because that's logarithmic. Okay, because we know we're looking for an exponential equation. Okay, now we've got two exponential equations, so how are we going to figure out which one we want it to be? Let's go pull some data points from this. What would these coordinates be? What are the coordinates there? It's 0, 2. Good job. And what are my coordinates for this last one? What are my coordinates for this last one? That's 5. I would say about 60, or it looks like it's maybe just off the line to me, so I would say maybe 65. Either one of those that you picked will be okay for us to check and see, because we're just wanting to see which one is the better model. Of these two exponentials, which one is the better model? So if I check P of 0, that gives me 2 plus 2 to the 0, okay? And 2 to the 0 is 1, so that's just 2 plus 1, which is 3. Okay, is 3 pretty close to 2? Yeah, it's pretty close. And remember, models don't exactly predict. And 3 is pretty close. So I'm like, maybe. Okay. If I try the other model, P of 0, that's 2 times 2 to the 0. Anything to the 0 power is 1, and 2 times 1 is 2. And that is our exact model. So that one's definitely okay for that one. But this one is close enough that I don't feel like we can differentiate between the models with that point. And that's why I went and grabbed another point at the other end of the graph, because it's further away. So we're more likely to see more of a change in our models there. So let's go check P of 5. Let's go check P of 5. So 2 plus 2 to the 5th. 2 to the 5th is 32. So 2 plus 32 is 34. Is that pretty close to our data? No, that's actually pretty far away, especially considering that we're in this semi-log plot. Okay, let's go check our other one and see if it does a better job modeling it. So P of 5 on that one will be 2 times 2 to the 5th. We said 2 to the 5th was 32. 32 times 2 is 64. And what do you think? Is that a pretty good? Yes, that's clearly the better model, so we'll pick D. Okay. Okay. Sorry for that. Okay, previously in topic 2.9, logarithmic expressions, we looked at the idea of using a logarithmically scaled axis to help us better understand the data that is exponential. We now return to this idea to examine it in a little more detail through using our semi-log plot. So again, we're doing a summary, a recap. It says in a semi-log plot, only one of the axes is logarithmically scaled. That's why it's called semi-log. Only one of the two is scaled. In AP Pre-Calculus, we'll only be scaling the vertical axis or the y-axis. With the semi-log plot, where the y-axis is logarithmically scaled, exponential functions will appear linear. And again, that's all recap, stuff that we've already talked about, okay? All right, so previously we looked at two graphs that displayed the population. This is literally the stuff from the last notes. This is the population of English Americans in the United States from 16 to 20 on a traditional graph versus the linearization that we get when we do it on a logarithmic graph, okay? The graph on the left, okay, and that's what it just says, so we could have skipped all of that too. All right, so here we go. Example 1. Use the features of the semi-log plot. Wait, am I on the... Oh, did I just read through that? Sorry, guys. I thought I went to the new page and all I did was scroll to the top. That's why I had to skip it all because it was all recap. Here we go. All right, we got to read through it anyway. All right, so an important note about semi-log plots. Okay, when we logarithmically scale the vertical axis for a semi-log plot, we are not changing the actual y values of the data. To logarithmically scale the vertical axis means that equally spaced values on the y-axis are proportional, whereas equally spaced values on the x-axis are linear. Okay, so we're saying that they're proportional rather than linear. We're not changing the data, we're just changing how we report the data. We're changing how we report the data. Okay, so it says, example 3, the table above gives selected values for the function f. Which of the following graphs could represent these data in a semi-log plot, where the vertical axis is logarithmically scaled? Okay, so taking a look at those, which two graphs should I be able to eliminate right away? Which two graphs should I be able to eliminate right away if they're asking which one is a semi-log plot? A and C, because those are equally spaced on the y-axis, and so those are linear. Those are those are not log plots. Those are not log plots. They're not logarithmically scaled. Okay, now we have two other choices, and these are both logarithmically scaled, but which of these is reporting our data correctly? On this first one, it's logarithmically scaled, but only to 10. How high does our data go? 203. And so that's why this one's not correct. Let's go make sure that this one is correct. At 5, we should be at 203. And at 5, we are at 203. So this one is the correct answer. This one's the correct answer. Okay. All right. Let's move it along. And also on that one, if you wanted to go back, I had looked at it just to show you a few more things. So I actually looked at it and I saw that this was changing additively. And this was changing multiplicatively by 3/2. And so I knew that this was an exponential function just looking at the data. And so looking at the data, its graph does look linear. And so I'm like, oh yeah, that's looking good. Okay. So I did look closer at it. It didn't turn out that we needed to look closer at it to tell which one was correct, but you could have looked more closely at that if you were, if you had two that were very similar. Okay. All right. We're going to skip this one. This is just plotting points. So you guys have done that before, but you can do it again if you want more practice with that. So that's just plotting on a semi-log plot, and the answers are on the notes key if you want to do that. Let's take a look at number 5. Okay, so it says plot the following data on both graphs below. So we're going to plot this data on both graphs. So let's get plotting. So this is a regular one. So we're going to have to change our scales here. So since we're going from 2 to 10, let's make our x-axis scale by 2. So let's say 2, 4, 6, 8, 10. And let's our y's, we need to get up to 115. So let's scale our y-axis by 20. So let's do 20, 40, 60, 80, 100, and 120. Okay, so using those as your scales, let's plot that data. So 2, 7, 4, 15, 6, or 5, 23, 5, 23, 8, 77, and 9, 115. 9, 115. Okay, and what does that look like? Yeah, it looks like exponential. That looks like an exponential curve. Okay, and then let's plot it on the semi-log plot. Now remember, that means we're not going to scale our x-axis, so that's just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now really important that I want to point out. Sometimes on our semi-log plots, they're just labeled 0, 1, 2, 3. Okay, but that represents 10 to the 0, 10 to the 0, which is 1. Okay, this represents 10 to the first, which is 10. And this represents 10 to the second, which is 100. And this represents 10 to the third, which is 1,000, Okay, so let's plot that data here. So we had 2, 7. And so remember, your bottom line is not 0. Your bottom line is 1, because that's 10 to the 0, which is 1. So that's 1, 2, 3, 4, 5, 6, 7. Okay. 4 to the 15. Now, when we hit that line, those are now counting by 10. So 15 is going to be halfway in between there. 523. So that's 10, 20, and a little would be 23. Okay. 8 and 77. So I'm going to go up to my 10. So that's 10, 20, 30, 40, 50, 60, 70, and almost to the next line there. And then 9, 115. So I'm going to go up to 100. And these are now counting by hundreds. So 15 is going to be down here at the bottom of that 100. Okay. On the semi-log plot, it looks linear. Okay. So linear on semi-log, which means it's exponential on regular. So linear on semi-log. Okay. So just good to kind of practice that again. I just wanted to practice, especially to make sure we understand the scale, because sometimes it is listed as 0, 1, 2, 3. But I want you to remember, even if they call it 0, 1, 2, 3, that's 10 to the 0, 10 to the first, 10 to the second, 10 to the third, or if you prefer 1, 10, 100, 1,000. Okay. Are we comfortable with the graphing? Follow-up questions on that? Okay, so it says find a regression equation for the data above. So we're going to put it in. What kind of regression are we going to do? Exponential regression. We're going to do exponential regression. So go ahead and put that in your calculator. Let's see your exponential regression. So we're looking for the a times b to the x, right? So that's going to be the a times b to the x. I think I want to help you with this. Do you guys care if I speed you up on this part? I feel like you've done enough regression that you don't need help on this part. So let's go ahead and let me give you that formula so we can move on to the part that's new. So we get 3.082 times 1.494 to the x. Okay, so that's our equation for exponential regression. So that's our exponential regression. Okay, it says take the log of both sides and use log rules to create a new linear function. This is new for us. We've never done this. So let's go see what they're talking about. They said take the log of both sides. So that's going to be log of y equals the log of 3.082 times 1.494 to the x. So we're going to take the log of both sides. Okay, and it says use log rules to create a linear function. Use log rules to create a linear function. Okay, so remember, the first day that we did semi-logs, we called the log of y. That's how you move data from regular XY data to semi-log data. That's how you move it to semi-log data. You take the log of the y value, and we called that a capital Y. Okay, so that's what they showed on the first day of notes. Since then, on notes, they seem to call it regular y again, but you need a way to differentiate if it's your y from your original data or if it's your y from your semi-log plot. So this is now clearly going to be on the semi-log plot because we took the log of it. So I'm going to go ahead and still put that capital Y there because that reminds me what that data is, okay? But just know that you may see a regular Y for it when you see it in some of their stuff, okay? So that's now my data changed to a semi-log plot, and we want to use this side to get this to be a linear function. So we've got capital Y equals capital Y equals, the log of a product can be written as the sum of logs, right? So that could just be written as log of 3.082, which could be our constant, plus if we have an exponential, what can we do with it? Bring it out front, so that could be x times the log of 1.494. Do you guys see that that's a linear function? Okay, we have a constant. This is like, and then we have our x, our variable times our coefficient. Okay, so that's the linear. So this would be the linear for the semi-log plot. So if you wanted to plot it on the semi-log plot, this would be the equation you would use to graph it on the semi-log plot. Okay, and that's what our capital Y is when we took the log of the regular Y. Okay. All right, so put those in our calculator to get decimal approximations for those values. We'll get that capital Y, which again is really just the same. They'll use regular Y, but that just reminds me this is for the semi-log plot, is 0.488 plus 0.174 x, and that's just evaluating these values in the calculator to get those decimal approximations. Okay, so that's the equation we end up with. So we'll star that and come back to that in a minute. Okay, then it says complete the table to find the log of y. So we're literally just taking the log of each of the y values, and then and this is where I had a mistake in class, which I think it was Vinay that caught. This is 1.1761 for the log of 15. So the log of 7 is 0.8451. The log of 15 is 1.1761. The log of 23 is 1.3617. Log of 77 is 1.8865. And log of 115 is 2.067. Then it says find the linear regression for the equation of x log y. So we want to pair x and log y. So let's get our calculators up and we're going to do a linear regression for that. So we did an exponential regression. This gave us the equation that we would have used on a regular graph. Okay, and now we're going to do a linear regression for x log y, which is what we graph on the semi-log plot. Okay, so on the semi-log plot, we graph the log of y, x with the log of y, as opposed to xy. So this is xy, and this is x log y. Okay. All right, so let's get that linear regression. So go to our TIs, and that's where I've got to fix that one point of data. Okay, so that's going to be 1.1761. Okay, and now I'm going to go to stat, scroll over to calculate. We're doing linear regression this time, and we're going to do choice 8 where we have the x in the back. I'm going to have it store it in alpha trace. We'll go ahead and put that in y1 and then have it calculate it. And we get 0.488 and 0.174 as the coefficient in front of the x. So let's take a look at that. So that would give us y equals 0.488 plus 0.174x. And that should look familiar because that is the same equation we got. That was the same equation we got when we took the exponential regression and just took the log of both sides to convert it to a linear form of exponential regression. And so that's what we're saying about getting this relationship between log and semi-log plots. We're not changing the y values. We're just changing the way that we present it. Okay, so all right, so hopefully that was interesting. Let's look a little bit more of that on one final example. Okay, so as we've seen, if we have exponential functions on a semi-log plot, the graph will appear linear. In these cases, we can create a linear model for the graph on the semi-log plot. And so rather than converting the data and then doing a linear regression, we can, it says given the exponential model, y equals a times b to the x, the corresponding linear model for the semi-log plot will always be y equals log base n of b x plus y plus log base n of a. Okay. All right. You can read that there. Sorry about that. All right. And two important things to know. So here, the coefficient on the x, that's our slope. Remember, that's our slope for a line. It says the slope of our line is always log base n of b. And so if we're thinking form y equals mx plus b, and we know b is the y-intercept, so the y-intercept is always log base n of a, log base n of a. Now, this y equals mx plus b, that's just our slope-intercept form of a line. This is not the same b as we're talking about there in the base, okay, but just showing you. So the y-intercept is always log base n of a, where the base n corresponds to the base being used for the scaling the vertical axis, which for us, n equals 10. We're using a base of 10 when we scale our y-axis. Okay, so let's take a look at this problem. It says the semi-log plot corresponds to the data table for example 3. So we've got example 3 earlier on in your notes. You can flip back to that data. Write an equation for the linear model for the semi-log plot of the form y equals log base n of b x plus log base n of a. Okay, so if we want to do this, we're trying to build a linear model. So remembering that's y equals mx plus b format. And so we know that log base n of b is just going to be my slope. It's just going to be my slope. The slope is the average rate of change. And so let's find the average rate of change. So the slope is the average rate of change. And so our data here, if we go back, let's see where that table 3 example is. Let's see if we can go back and find it. Example 5, 4, there he is. There we are, example 3. So here's that data that we're looking at. And so at 1, it's at 40. At 5, it's at 203. Okay, so there's that data. And so we're going to use the points. We don't need any 2 points, so let's just use those first two. That'll be easiest to do, 140 and 260. Okay, so from the original data, 140, and I'll go ahead and write it here. Actually, let's not put it there. Okay, so those data points, those 2 data points that we're going to use were 140 and 260, and this was from example 3, so you can go back and look at all that data in the table if you want. But we know the average rate of change. Now, we're trying to get the linear form, which is for the semi-log plot. So we don't want the regular y values. We want the log of those y values. We want the log of 40, and we want the log of 60. So we're going to do log 60 minus log 40 over, what was the change in x? It was 2 minus 1. Remember, our x's aren't scaled, so they're not different. They'll stay the same. But we did scale our y's logarithmically, so we have to use the new y values. And since 2 minus 1 is 1, then we can just, that's just the log of 60 minus the log of 40. And if we do that in our calculators, we'll get that that's approximately 0.17609. 09. Okay. And that is going to be our slope. Okay, so if we start building the equation, we've got y equals 0.017609 x plus, we said it's going to be the log base n of a. So our base is 10, so that's just going to be a common log of a. Okay, and so now if we plug in our specific point, so if we go ahead and plug in our log 60 as our y value there, we've got the log of 60 equals 0.017. Oh, wait, I put my decimal in the wrong place. My apologies. We got to catch our mistakes. So I went to copy that, and I see I put that in the wrong place. I'm not used to putting the 0 out front. I'm trying to do that for you guys since most of you seem to like to do it that way. I usually just start with my decimal. So, but catching your mistakes is a good thing. Okay, so I've got the log of 60 equals 0.17609 0.17609 times our x value. What was the x value that paired with the log of 60? That was 2. Color change that to 2. Okay, plus the log of a. Okay, and so if we multiply that out and subtract it from both sides, we get that the log of a which is log 60. I'll write it out here for you. Log 60 minus 0.1. It's hard to change habits. 0.17609 times 2. The log of a is approximately 1.425 ... Okay, so now we have our two values. And so we can go ahead and put them together. So they asked for write an equation. So let's go ahead and get our equation written. So it's going to be y equals 0.17609 ... because we would still use the full value, x plus 1.425 ... So there's our linear model. Okay. So we just found the slope, and then we found the y-intercept using that point. Once you know the slope, you can plug in a particular point and you can solve for the y-intercept. And so that's what we did, but just with our log values. Okay. All right, then it says use the linear model from part A to write the equation of the exponential model. Now this is interesting. So in the last example, we started with an exponential model and we used log properties. We took the log of both sides and used log properties to convert it to a linear model. Now we just found a linear model and we're going to convert it back to the exponential model. And that, by the way, is why we didn't just use our calculators to get the model for us, because they were wanting us to practice going in the other direction here. Okay, so let's think about this. We know two things. We know that this is in the position of log base 10 of b, and it's base 10 because we chose a scale of 10 on our scale on our y-axis. And we know that this, and I'll go ahead and write that, log base b is 0.17609. And we know that this is log base 10 of a. So this is log base 10 of a. And of course, you don't have to write the 10 if it's common log. We can just write that. So that's 1.425 ... Okay, so how can we then get the a and b values to plug into our model y equals a times b to the x? Well, this just means 10 to that power gets us b. So b is just 10 to the 0.17609. And if you put that in your calculator, you'll get that that's about 1.5. And 10 to that equals a. So a equals 10 to the 1.425. Okay. And that was just my little dot connected over there. So that was just a little manual typo. Okay, and if you put that in your calculator, you'll get that that's 80 over 30, or 80 over 3. And so then I can put those together in the format y equals 80 over 3 times 1.5 to the x. Okay. So it might have felt like we were going about this part the roundabout way, but that was just them wanting to take you through it in this order. Okay, so you can go in either direction. Hope that helps.